Today I want to talk a little bit about how language models learn to do all the fancy things that they do. Let's start by reminding everyone that a language model's job is to predict the next word. Chicago is often called the Windy City. Mount Rushmore is in South Dakota. Batman's archenemy is the Joker. The notion is that these models look at a piece of text, predict the next word based upon the words in that text, and then add that word to the words that it will use to predict the next one. And they do it really well. So after Chicago is often referred to as the Windy City, the system continues, reading its own output as input and producing, due to the strong winds that blow off Lake Michigan, particularly in the downtown area, and so on and so forth. These models are really all about language. They're language engines in that they predict words. They're fluency engines in that they use larger and larger sets of words to guide and fit the words they are generating to the context they've seen. They're category engines in that they have encoded relations between words like cat and dog and hamster and words like pet and veterinarian. And they are what we call completion engines in that they use their input as the starting point for the next words they are going to generate. So how do they do this? How do they know so much about the relationship between words that they can predict so well? The answer, of course, is that we train them. We train them with a lot of words. One thing to know about machine learning is that when you are trying to train a model to predict something, you usually have examples that have two components: the data that the system will see in the future and the target that you want it to learn to predict. If you're training a system to recognize cats, you give it pictures of cats where each is labeled as cat. And you give it pictures of things that aren't cats, labeled as not cats. With enough examples, we can then show it a new picture, and it will recognize the similarities between the new picture and the ones it has seen before, and, depending upon the match, say cat or not cat. If we're using text, the words tend to be the data. We train with text like, the new superhero movie broke box office records grossing over $500 million worldwide in its opening weekend, labeled as entertainment. Then we give it the Prime Minister's recent speech on the economy received mixed reviews, with some praising her proposals while others criticized them as inadequate, labeled as politics. Once you do this for a few 100,000 examples, the system figures out which words and word combinations predict different categories. But what are the labels for language models? Well, we want to be able to predict the next word. So we want to be able to say, given this text, this is the next word. And in training, we want to be able to do this millions upon millions of times over. Large language models need to be trained on a lot of documents. These documents come from the web or other sources. But most of the 6.2 billion pages on the web are not tagged. So how do you figure out what the target for my prediction is? I can't just give it a page and say, here, learn something. So there's a trick to it. If you want to predict the next word, you can treat chunks of words in a document as the input data and the word that literally follows them as the target. Then you move your window of words to include the word you just used as the target as part of the next input, and pull the following word in as the new target. With this, we get to take a document about the Eiffel Tower and train by telling the system that given the text, the Eiffel Tower is a wrought iron lattice tower located in Paris, and so on, through the tower stands at a height of 324 meters, making it the tallest, and the next word is structure. And then after structure is in, and then Paris, and then period. We simply use the words that come before to train the system to predict the words that come after, one word at a time. The amazing thing is that we can do this without any supervision. Once you have the mechanism that takes a piece of text, chunks it down into individual words or tokens, and then uses the tops to predict the bottoms, we can run that without ever looking at it again, for as many documents as we want, for as many words as we want. The training links the words that have been seen to the words they predict. And what do these systems learn? First, that words predict words. Words like pasta, marinara, Caesar, salad, wine, each predicts dinner. A bit on their own, but together a lot. And it doesn't really matter what order they come in. Next, they learn that the different orderings of words predict different next words. We are having pasta with marinara and a Caesar salad on the side. What sort of wine should I have? Is different than. Is Chianti a good wine to go with pasta with marinara and a Caesar salad? Same words, different order, different predictions. And that depending upon the context, one word may actually be different words. Consider the sentences. She had a part in her hair. She had a part in the play. She had a part of the puzzle. The word part here really has different meanings and different encodings. A feature of hairstyle, a role as an actor, and a piece of a puzzle. These systems learn all these elements and how they interact with each other in combination. It's the combinations that make things interesting. When we talk about the size of a language model or its number of parameters, we are talking about its capacity to encode the relationships between the elements defined by the words, their positions, and their different meanings in context. For example, the phrase White House predicts political words far more than either white or house. The phrase is more than the sum of its parts, and we need to capture that interaction. So we need to record it somewhere, and that's part of what our parameters do for us. The greater the capacity, the larger the input window, the more we can capture and the better the predictions will be. OpenAI's GPT-3 had on the order of 175 billion parameters. GPT-4 has approximately 1 trillion parameters. And as we grow larger and larger systems, they have more and more of these parameters, and they're encoding more and more of the relationships between the words that they've seen. The overall quality depends upon more than the structure of the model, though. The quality of the corpus, the documents that are used to train the system, determines the quality of the predictions and the writing. As with all machine learning systems, the past determines the future. Likewise, the sheer volume of the training set is important in that errors coming from some documents can be corrected with the weight of the others. And the greater the breadth of the content, the greater the breadth of the model and its generation. And finally, the number of tokens or words that can be included in the input. The more context that a system can be trained to respond to and use in predictions, the more fluent the system will be. The result is a system that can use the context of larger and larger sets of words to generate more and more fluent text and response. The result is language engines, fluency engines. We'll talk more about this later, but it's important to see that they are exactly what their name implies. Large language models, not search engines. There is no place for them to remember the documents that could be searched, not databases. There's no place for them to remember the data either, not reasoning engines. They predict words, and certainly not repositories of fact. They know the relationships between words. They know how to say things, not what to say. Thanks for listening. And please, stay safe.